Hello and good evening. My name is Scott from the University of South Florida. This is calculus class. It's the 1st of October 2020. And tonight we're talking about implicit differentiation. So warning, heads up, alert, alert, alert. This is probably, I want to say it's the simplest but hardest topic. It's not the simplest but hardest. It's the most simple but hard topic that we're going to cover, that you really need to understand in order to get stuff out of it, in order to do well on the test and get stuff out of it. There is simple but hard stuff that we cover that that I'm doing to plant seeds, but this is a simple but hard, a very simple, very hard concept, or very simple but hard concept. That some people are just like, well, duh. I was not one of those people. This was incredibly difficult for me to understand why you can do this and how this works. So again, some people are just like, they breeze right through it. But I mean, the fact that I've introduced the topic in an activity, that you're doing a peer leading activity on it on Friday or tomorrow, and that I've put a lecture on it dedicated pretty much entirely to it, demonstrates how important this topic is. So again, tonight, this evening, very, very simple, but very, very difficult idea or at least it was for me. Now, whether or not you, grasp it very quickly, some people are just like, oh, what are you talking about? This is so easy. Okay. Good for you. Good for you. Okay. So let's, get started. So last time we talked about the chain rule, and the implicit differentiation is basically an application of the chain rule. So, and the thing that everybody does first is the circle. So last time we talked about implicit differentiation, the chain rule. And tonight what we're going to be talking about is, where can I do implicit differentiation? Why does it work? And what can it do? And then look at this list, okay? It does a lot. And a lot of these things that, a lot of these things on this list are very important. This is module 2. This is module 2. This is module 2. This is the beginning of module 3. This is in module 2. Actually, I think this is at the beginning of module 3. Anyway, and then all of these things in science, economics, all of these things where we don't really have a function, we can still do a lot of derivatives and interesting things on them, even though we don't technically have a function. So if we can draw it in little areas. So the example of this is always x squared plus y squared equals 1, the circle. And what I want to do, problem, find the slope of the tangent line. At some x and y. Okay, so on the packet I did, on the packet it was, at the point square root of 1/2, square root of 1/2. But we don't have to do that point. So let's look at the point. So let's find, in particular, let's find it at 1/2. Let's see. If I'm at 1/2, if x is at 1/2, so let's find it right here. So that says, here we will do, x is 1/2. That would mean y is the square root of 3/2, or the square root of 3/4. Okay, or root 3/2. Okay. So again, the problem is find the slope of the tangent line at some x and y. Now, the question is, I mean, it's clear this thing has tangent lines. After all, that's why we call them tangent lines, right? Tangent line, the whole concept of a tangent line refers to the circle. So the tangent line here is going to be the thing that touches the circle at one point, and it's perpendicular to the radius. And it's the thing that does this. So how do we feel about the, oops, didn't want to do that. How do we feel about the concept of the tangent line, 1 to 5 at this point? What's the line I'm looking for? 1 to 5, how do we feel about that? That was a little too far. Okay. All right. So this is the problem. I want to find the slope of the tangent line. Or the line tangent. Okay. Well, there are a couple ways I can do this. Method 1. Let y equal. So I'm talking about I'm talking about this piece of the curve. So method 1 would be let y equal the square root of 1 minus x squared. And so what I'm going to do is dy over dx equals, and now I'm just going to do the algebra. I mean, I'm going to do the calculus, right? I'm going to do the derivative d over dx of y, which in this case here is 1 minus x squared all to the 1/2. So I'm going to let this be my u. And what I'm going to get is I'm going to chain it. And so what I'm going to get is d over du of u to the 1/2 times d over dx of u. And that equals here, let's see, this is going to be 1/2 u to the -1/2 times the derivative d over dx of 1 minus x squared, which is going to equal 1/2 u to the -1/2 times, this is going to be 0. The derivative of this is going to be 0 minus 2x. And so I wind up, and then I sub back in my u. So my u was 1 minus x squared. It's on the bottom with a square root. And I've got 2x here on the top. Okay, and obviously the 2's are going to cancel. And I wind up with negative x over the square root of 1 minus x squared. How do we feel about that 1 to 5? All right, I did a chain rule. I did some messiness with the u's. I played with it some, and I wind up with this. And so what I want, because I want the slope of the tangent line at 1/2 negative, I'm going to plug in for x. So dy, let's get rid of the ruler here. Dy over dx, when x equals 1/2, is -1/2 over the square root of 1 minus x squared 1 minus 1/2 squared, which equals -1 over, so this is going to be a -1 on top. I'm going to move that 2 to the bottom here. 2 times the square root, now this will become 1/4, so that becomes 3/4. Okay, I pull out the 3, and I pull out the 4 on the bottom, and I get 2 times 1/2 on the bottom times the square root of 3. And I do the 2 and the 1/2 cancel, and I wind up with -1 over the square root of 3. Okay. So that's one way I could approach this problem, right? I'm going to find the slope of the tangent line. Okay, I need dy over dx. Okay. Well, I'm viewing this very geometrically, of course. But there's another way to do it. And the other way to do it is to implicitly differentiate. So what do I mean by this? So we'll say this is the other way. So what I'm going to do, this should not be showing up yet. Let's move the folium down. That's the next graph. Okay. The other way is to do it implicitly. So what I'm going to do is I'm going to take the derivative of both sides okay, in terms of x. I should say I'm going to set f of x equal to y. May not be needed. And then take the derivative of both sides in terms of x and then solve for dy over dx. Now, this first step will not be needed a bunch of times. So tonight, we might get to the places where I need it, but I might not. But if I need it, I need to set f of x equal to y. But I don't need to do that here. So my curve, implicit way. So my curve is x squared plus y squared equal 1. So now I'm going to take the derivative of both sides with respect to x. So d over dx of x squared, I'll actually do it the whole thing, plus y squared equals d over dx of 1. Now, one of the great things about doing it this way is that one side usually, especially if I've got constants, easy. And even if I have some complicated quotient, one of the big advantages of this way is I can actually get away by just taking the bottom and scooting everything over to the other side, if the other side was something constant, and then not have to deal with the quotient rule, especially if I've got something like a long rational function. I could just like... So, it depends what you've got. But here what I've got is, on the left side, I've got x squared plus y squared. And here I've got this. Now, I'm going to break the left up with the sum rule, and the right, what happens to the right side? The right side becomes 0. So now I've got d over dx of x squared plus d over dx of y squared. Now, this is an x, and this is an x. So now this is an x, and this is an x. Well, that's easy. I use the little power rule, and I get that this right here is 2x plus. Now, this is harder. Here you see I've got an x, here I've got a y. Now, recall our chain rule. I'm going to rewrite it in different terms. I am going to write d s over dq equals ds over dr times dr over dq. And I'm doing that because I don't want to confuse the x's and y's. So this right here, y squared is my s. But notice this right here is not in terms of q. It's not in terms of my x, right? It's got the wrong variable. So I have to apply the chain rule. The chain rule is the thing that allows me to do this. Okay? So what I'm going to do is apply the chain rule. And I wind up with the following. I wind up with d over dy. I change the x that I'm differentiating in terms of to a y times y squared. And then I need to account for the change in y given the change in x. So remember, the chain rule is the thing that lets me convert this x to a y. So I change from d over dx to d over dy. And when I do that, that's the thing that generates the dy over dx. So now I wind up with 2x plus 2y, because the derivative with respect to y of y squared is just 2y, times dy over dx equals 0. And now I do a little algebra. I'm going to solve for that dy over dx. So I'm going to move u over here, and I'm going to wind up with 2y times dy over dx equals negative 2x. Divide both sides by the 2y, and I wind up with dy over dx equals negative 2x over 2y. The two 2's cancel. And my final answer I wind up with is negative x over y. Okay. Well, we call y that y equaled 1 minus x squared. So this actually equals negative x over the square root of 1 minus x squared. And I wind up with the same answer. It should be noted that these are very general directions, but here I don't actually need the subend for y. And this is if needed, by the way. Because what did I want to know? I wanted to know I wanted, where's the thing? I wanted slope at a particular number. I wanted the slope at 1/2 square root of 3/4. Okay? So I actually don't need the sub in. Right? I can actually use just this piece. So with this piece here, oops, I don't want to do that. I want to copy it. There we go. And with this piece here, I can actually do everything I want. Why am I doing that? It's faster just to write it. So with those two pieces, I can actually do everything I want. Okay? So if I've got that, that means that dy over dx, when x equals 1/2 and y equals the square root of 3/4, equals -1 over 2 over the square root of 3/4. Okay, this right here is going to be the square root of 3/2. Okay, and the 2's cancel, and I wind up with -1 over the square root of 3. Which is what I wound up with here. So how do we feel about that trick, 1 to 5, about implicitly differentiating? One to 5, how do we feel about that trick? Okay. All right. Well, there's two things that are weird about this. Why can I do this? Well, the reason I can do this is something called the implicit function theorem. All right. And the implicit function theorem basically says the following. It's a Calc 3 concept that we're kind of importing this. Can we go directly to the purple writing to set up the equation? No, you have to do the derivative before you sub in the constants, if that's what you're asking. If what you're asking is, can I start here, the answer is yes. The question is, can we go directly to the purple writing to set up an equation? Okay. So the implicit function theorem basically says this. Let's see. Paraphrased. If I can zoom in on a graph sufficiently, so what I see passes the vertical line test, graph centered on x. sufficiently so that what I see passes the vertical line test, then I can take the derivative of both sides at that x. Okay? That's what the implicit function theorem says. Paraphrased. So what do I mean by that? Okay. Well, what I mean by that is this. Here is my circle. Now, if I'm looking right here, or right here, this was the point we had before, 0.5 here. Now, right now, I can't do it. Right now, I don't have a function. But if I can zoom in, x is 0.5, there it is. So if I can zoom in enough so that now I have a function, I can do this at x equals 0.5. Right? Because now, if you look at it, what I'm looking at passes the vertical line test. 1 to 5, how do we feel about that? Where can't I do it? Well, if x is 1, look what the problem is. If x is 1, there's no amount of zoom I can get to get rid of that vertical line. Right? That vertical line is always there. If x is 1, I can't pass the vertical line test. However, anywhere else on my graph, right? Anywhere else on my graph, let's do point, that's way up here. Let's zoom out a little bit. Let's do this point, this x value right here. That's not quite 1. Oh, it's not going to let me select that. This one. So let's do 0.999 here. 999 here. I can zoom in enough, and as a matter of fact, I can zoom in just using one of the axes. I can zoom in enough that eventually I can consider it and have a function at that point. But I can't do that at 0, right? No matter how much I zoom in, I'm never going to pass the vertical line test here. All right? No matter how much I zoom in, I'm never going to pass the vertical line test. Okay. Now, the other part of this is to remember to do the y, is to remember the chain rule. The other thing that's hard about this is remember the chain rule. This is a brand new nib, and it's already gone. Not only is it a brand new nib, it's a brand new nib. It's a brand new OEM nib. It's from Microsoft. Yeah, at least I think it's from Microsoft. Maybe I got a fake one on Amazon or something. Okay, the chain rule is what lets me change the variable. So, anytime I am differentiating, anytime I encounter something that is not on the bottom of my differential symbol, I generate a derivative. I generate a derivative term, okay? So, for example, okay, examples. D over ds of t squared, different. This is going to be 2t times dt over ds. Right? These two are different. D over d v of u plus v equals different, same. Now, I'm not saying any of these are constant, right? They're not constant. These are all moving. Right? If it's a constant, it just goes to 0. But if it's not a constant, if it moves, I need to use the rule. So this is going to be 1 times du over dv plus 1. Another example. D over dz of x times z equals, and I need a product. Okay. Now, this right here, I'm going to do the first derivative of the first times the second plus the second. I'm sorry, the first times the derivative of the second. And notice I'm still differentiating in terms of z. And Laura's very proud of me right now in chat for not saying z. That's going to equal 1 times dx over dz times z. The 1 came from that first one. Plus x times 1. Okay. D over dq of r cubed plus 3q is going to equal the derivative of the outside, 3r, times the derivative of the inside. Remember, that's a chain rule. And then I'm going to have plus 3. Okay, how do we feel about that? 1 to 5. Every time I encounter a variable, a non-constant thing, right? If it's a constant, it's just 0. But every time I encounter a moving variable that is not the variable by which I'm differentiating, I'm going to generate another one of these terms. 1 to 5, how do we feel about that? If you want to do it mechanically without understanding, just remember down here, and this is actually why I have been using the the operator notation the entire time, because the operator notation tells you what you're differentiating with, and that's very important. Some people don't like it. I didn't like it when I first encountered it. I was like, well, why? Prime's perfectly good. Prime's okay, except it doesn't tell you what you're differentiating in terms of. This always does. That's why I like it. It makes explicit the implicit. I like that. All right, let's do another example. This is called the Folium of Descartes. This particular Folium of Descartes, the equation here for this line, for this curve here, is x cubed plus y cubed equals 4xy. This is called example. The Folium. Am I spelling that correctly? Yes. By the way, this one's also in your book, but the thing's a little different. The equation's different. So, if I wanted to talk about what first, questions. Where can I not differentiate? Yes, I'm sorry. You're right. 3r should be 3r squared. I'm focused on what I'm saying, not on what I'm doing. Okay, so where can't I differentiate here? Well, there's going to be a point here that I'm going to have a vertical. So there's some point in here that I can't do it. And then this point right here is just bad in terms of everything. Okay. At 0, 0, I can say nothing, right? I've got everything going wrong here. I've got a horizontal, I got this thing crossing. So I don't know if you mean to curve up like this. So I could say something if you wanted to curve down like this, but I don't know that's the path you're talking about, the derivative, because I could be going like this. So one of the things you'll do in Calc 3 is you'll have parameterizations of these things. And that's actually where the implicit function theorem comes with. I'm going to have this will be expressed as a function of two variables. As a function of time with an output. And that I can actually do derivatives on, because then I get kind of what's going on at the time. But at this point, we don't have that information, if that makes sense. So right now, it's bad in terms of everything. Okay. The other problem here is that I'm not going to be able to solve this for y very easily. I mean, I kind of could. I would have to break it up. I'd have to do it on domains. This is kind of a lousy thing. So how do I find? So question 2, find the slope of the line tangent to 2, 2. Okay. So I want to find this line right here. Okay. So what am I going to do? Well, nope, go away. I've got x cubed plus y cubed equals 4xy. So I'm going to take the derivative in terms of x of both sides. Now, all right. So the derivative of x cubed over here, I messed it up earlier, so let's try not to do that again, is going to be 3x squared. And now I'm going to take the derivative in terms of x of y cubed. Let's just leave that unevaluated for the moment. Now, on the right side, I've got a product rule, right? Because I've got x, I'm going to pull out the 4. And then I've got a product rule, because then I've got d over dx of x, y. So my journey of x looks like the following. I've got an x. On this side, I've got an x, and I've got a y. So I've got an x that becomes a y. I don't know how. So I've got an x becoming a y, because I know y moves with x. I don't know how. And then I've got kind of a y cubed going on here, and I've got an x cubed going on here, and then I'm adding them together. Now on the right, I have an x, and I have an x, and one of these x's becomes a y. I don't know how. It just does. And what else is going on here? I got a 4 happening here, but I'm shoving x and y together. So I've got a product. And then I'm just kind of multiplying it by 4. Right? So this is going to be a constant multiple rule. This, right, and I could have made this 4x if I wanted to. That would have been fine too. But the 4 is going to wind up factoring out of all the terms anyway. So I'm going to let it be. This will be a product. This is a sum. And these are going to be chains, right? Because I've got a y cubed becoming a y. I've got an x that became a y that became a y cubed. So how do we feel about those journeys? I've got a journey of x on the left, and I've got a journey of x on the right. Okay. And this idea that x just became y. I don't know how it happened, but I knew it happened. I know that when I wiggle x, it's going to wiggle y. Right? Somehow x affects y. If I wiggle x, I'm going to wiggle y, which is going to wiggle y cubed. Okay. So what I'm going to do here is I'm going to do the thing. So right now I've got 3x squared plus, now I'm going to use a chain. I have an x here and a y here, and I can't do anything about that. So I'm going to do d over dy of y cubed times d over dx of y. And that's going to equal, now I've got this 4 hanging out by the constant multiple rule. And now I have to do a product. So I'm going to do the derivative with respect to x of the first times the second plus the first times the derivative with respect to x of the second. Okay. Well, now I've got something going here. Now I've got a y and a y. That's okay. So I'm going to wind up with 3x squared plus 3y squared times the derivative of y with respect to x. Well, that's dy over dx. Equals 4 times the quantity. Now, the derivative with respect to x of x derivative with respect to y of dx of x. I'm sorry. The derivative of y with respect to x is dy over dx. Okay. Now, I could solve, but I don't have to. So if the question asked me to solve for dy over dx, I could, but it didn't. Okay, now I've got the y I want and I've got the x I want. So now I'm going to plug into 2. So now I've got 3 times 2 squared plus 3 times 2 squared times dy over dx equals 4 times the quantity, well, 2 plus 2 times dy over dx. Now, if I wanted to solve explicitly for dy over dx first, right, I would multiply the 4 out. I'd wind up with 4y plus 4x here, right? Then I'd have to divide things. It's doable, but it's unpleasant. I want to solve for dy over dx, so I get all the terms with dy over dx on one side, and all the terms without it on the other. Right, so if I wanted to, I would do this. I would have 3x squared plus 3y squared times dy over dx equals 4y plus 4x dy over dx. And that's going to become, the y moves over there, that term. Let's do this one here. So I'm going to move this term over here and this term over here, and I'm going to wind up with 3y squared times dy over dx minus 4x dy over dx. So I isolate the dy over dx terms. I get 4y minus 3x squared. And then what I'm going to do is I'm going to factor and solve the divide here. So I'll get dy over dx times 3y squared minus 4x equals 4y minus 3x squared. Then I divide both sides by that, and I wind up with dy over dx equals 4y minus 3x squared over 3y squared minus 4x. So if you must, that's how you do it. But I don't have to because it didn't ask me to do that. What I did was plug in x and y, and I wind up with the following. So this is 4, that's going to be a 12. That's 4, that's going to be a 12 dy over dx equals 4 times 2 plus 4 times 2 dy over dx. This becomes, this is an 8. This is an 8. I'm going to move that 8 over there. So this becomes 12 minus 8 equals, what did it do? 12 equals 8 dy over dx minus 12 dy over dx. So I move that 8 over there, that 12 over there. And I wind up here with 4 equals, I should have divided out the 4s at this point. Matter of fact, I should have done that all the way from the beginning. I should have just divided out the 4s. Oh well, negative 4 dy over dx. The 4s will cancel. And I wind up with dy over dx equals 1. Negative 1. Okay. How do we feel about that process, 1 to 5? So I've done a lot of examples here. And again, there are even more examples to be found on the problem set, on the packet, and all of those things. Okay. But this process is very, very powerful. Okay, so I can get at stuff that I really can't get at otherwise. And I have simpler algebra usually. So let's do the power rule for rational exponents. So let's prove it. Okay, so this is why it's powerful. Let's do an example. Okay, let's say I want to do the square root. So let's do d over dx of the square root of 2. Okay, this is the problem. Find dy over dx for the square root of 2. Only having the power rule for integers. So on the last problem set you proved, or the problem set that's due tonight, you proved the power rule for negative exponents, right? For negative integer exponents. So this is the power rule for fractional exponents that are nice fractions. Rational things. So what am I going to do here? Solution. So what I'm going to do is I'm going to set y up. Should not be a 2. Go away. So my solution is I'm going to set y equal to the square root of x, square both sides, and then implicitly differentiate. Okay? This is very slick. All right? So what I'm going to do is I'm going to do this. So y equals the square root of x, and that gives me that y squared equals x. Now, I have the power rule for integers. So now I take the derivative of both sides. In terms of x, d over dx of y squared equals d over dx of x. Kind of cool. Okay. Well, now what do I do? Take the derivative. This means that 2y different times dy over dx, because they're different, equals 1. Well, that means that I move the 2y over here. I've got dy over dx on one side. Let's move the 2y over here. So that means dy over dx equals 1 over 2y. Now, since I made y, right? If I giveth, I taketh away. Okay? Go feel like God. If you giveth, you must taketh away. Okay? So, since I giveth, I must taketh away. So, y equaled the square root of x. So that gives me that dy over dx equals 1 over 2 root x. And I'm not saying I am God. I'm saying you are when you do these problems. And when you giveth, you taketh away. If you createth, you destroyeth. Or sub back in. And that's it. I've now, without using the power rule for in general, only using the power rule for integers, I've solved this problem. 1 to 5, how do we feel about that? All three of you, how do we feel about that? That good, huh? Okay. Well, let's do another one. So let's do d over dx cube root of x. Okay. So y equals, I'm going to create a y, the cube root of x. And that means that I cube both sides, I get y cubed equals x. Take the derivative of both sides, I get d over dx of y cubed equals d over dx of x. Very nice. Okay. Well, that's going to give me 3y squared dy over dx by the power rule in the chain rule equals 1. And that gives me that dy over dx equals 1/3 times 1 over y squared. Which equals, since y equals the cube root of x, 1 over 3 cube root of x squared. How do we feel about that, 1 to 5? Kind of a nice little thing. Well, let's do it in general. Let's do it for any integer k, any positive integer k. We can actually do it for negative integers k. So let k be a positive integer. Okay. Compute, or I should say prove that d over dx of x to the 1 over k equals, and what do I want? 1 over k times x to the 1 over k minus 1. Okay. Let's do it. Okay, so let y equal x to the 1 over k. Then y to the k equals x. I'm going to take the derivative of both sides. D over dx of y to the k equals d over dx of x. This right here will equal k times y to the k minus 1 times dy over dx. And that equals 1. Okay, well, let's put that over on the other side. And we wind up with dy over dx equals 1 over k times, now I'm going to do 1 over y to the k minus 1, but I want that whole thing to be on top. So what I'm going to do first is I'm going to do this. I'm going to multiply through a -1 and I'm going to stick it on top. And the reason I'm doing that will become evident in just a moment. Okay, well, remember y equals x to the 1 over k. So what I'm going to do is that this equals 1 over k times x to the 1 over k to the -k plus 1. Now, remember what happens when I deal with these things. Okay? When I have these when I have exponents, recall x to the a to the b equals x to the a times b. So that is going to equal 1 over k times x to the 1 over k, 1 over k times -k plus 1 over k. Well, that's nice, because then those fractions are going to cancel, and I wind up with 1 over k times x the k's cancel, and I wind up with a -1 plus 1 over k. And of course, since I can just switch that around, it's 1 over k, x to the 1 over k minus 1. How do we feel about that proof, 1 to 5?